Welcome back once again. Another section in physics we'll be talking about is machine. Machine is a very vital topic in physics that you need to understand. When you talk about machine simply means a tool or tools used or needed to make work easier. You apply them to make work easier, more convenient, and more effective. For example, in terms of transportation, if a moving vehicle is a machine, imagine those days they use what we call the beast of burden, following a camel or horse from the south to the north. Is more tedious and time wasting. So we now have modern machines like the vehicle moving fast at a very high speed because they are well designed. Okay. Now we have machine. Simple machine. Remember, we have complex machine and simple machine. Complex machine, meaning they need more critical thinking in terms of their designs. So for simple machines are tools needed to make work easier by changing the direction of the forces. The direction of this force, either it may be in the clockwise direction or in the anti-clockwise direction. So definitely, machines are tools needed to make work easier, more convenient, more efficient, without stress, with ease. So they make work easier by changing the direction of what? Of force. For example, simple tools at home like the knife, the scissors, the nutcracker, the bottle opener, those are classified under the lever. So levers are simple what? Are simple machines. And they are of different type. From your elementary physics of different types, you talk about the first class lever, the second class lever, and the third class lever. Then you have wheel and axle. The wheel and axle applications, maybe your car steering, the wheel steering, or maybe the one you have in your well, or sometimes building constructions. In building constructions, sites, if you want, they are mostly used to lift load from the ground, maybe to a particular height of about 50 meters. You have the wedge. Maybe you have two inclined planes, serve as a machine. The inclined plane, for example, I have the trunk. If I have the trunk of a truck, for example, maybe I need to move this drum. If I need to move this drum away from this trunk, so I have to maybe I have two flat wood, for example, can be placed I can be inclined at an angle at the back of the trunk of a truck. So what happens? The drum containing diesel can be rolled downward, or while trying to load the truck, can be rolled upward. So majorly we have pulley, we have lever, we have the screw jack, we have the wheel and the axle, we have the wheel and the axle. Like the screw jack. The screw jack is mostly used in lifting of load. Maybe you want to lift a car up, you have a flat tire, you want to change your flat tire. There is need for what? For the screw jack. Okay, now there are major terms. That are conversant with machine that we need to know. So what are those terms? in machine, you must talk about the efficiency of a machine, then the mechanical advantage, then the velocity ratio. So we must talk about the efficiency of a machine, the velocity ratio. Okay. Now, efficiency. If we talk about efficiency, we know that efficiency is the output over input. For example, we can say distance moved by load over distance moved by the effort. Okay, distance moved by the load over distance moved by the effort. Or definitely we can say that efficiency is MA over VR times 100% over 1. What is MA? MA is mechanical what? Advantage. Mechanical advantage. So what do you mean by mechanical advantage of a machine? Now the mechanical advantage of a machine is load over effort. Load over what? Effort. So mechanical advantage is load over what? Over effort. Now what is velocity ratio? Velocity ratio is effort over load. Now, sometimes if we need to reduce effort, that implies that the mechanical advantage will be greater than 1. Mechanical advantage. Okay? If mechanical advantage is greater than what? Than 1, it means we have reduced effort. Now, most machines are being designed so as to reduce what? Effort. For example, like the screw jack. The screw jack is a kind of machine. Now, we know that for screw jack, the mechanical advantage is 2 pi r over L, over the pitch rather, the distance between the thread. Then velocity ratio is 2 pi L over the pitch. Now, for a screw jack to lift a very gigantic load, like a car, okay, what happens is that little effort is needed to lift load. Little effort is needed to lift heavy loads. So in that case, such a machine has a mechanical advantage. For example, you have under the lever, we have under the second class, we have what we call the wheelbarrow. Now, the wheelbarrow is designed in such a way whereby the load is between the fulcrum and the effort. So what happened? The wheelbarrow is able to lift a very gigantic load or very large load. Imagine wheelbarrow can carry up to maybe 7 or 8 bags of cement, for example. So the mechanical advantage of a machine is designed in such a way whereby to reduce, if it's greater than 1, is to reduce effort. But if mechanical advantage is less than 1, is to increase speed. Is to increase what? Speed. In such scenario, that means we have the wheel and the axle. The wheel and the axle is put into consideration because at that point we need more speed, like the movement of the bicycle, for example. Now, what happened is that there is a reduction in the movement or in the rotation of the pedal of the bicycle. But what happened to the wheel? The wheel is moving at a very high speed. Now, because the wheel is moving at a very high speed, the mechanical advantage is less than 1. So if the mechanical advantage is just 1, if the mechanical advantage is just 1, that means there's no gain. There's no gain. So efficiency of a machine is mechanical advantage over velocity ratio times 100% over 1. Now again, the velocity ratio can come as a form of the rotation of a pulley. Sometimes it's given maybe as 4 or 6 or 5 and so forth. Okay. Now another popular question that may be asked maybe in the JAMB and in the WAEC. Remember, this video is brought to you by O3 School JAMB app. Our major target is 300 plus in your JAMB forthcoming exams. So what we are saying is that there are most of the question that is coming from the machine. Now, what does that mean is that sometimes we have losses. We have losses when in mechanical advantage, we have losses. While in velocity ratio, losses are not put into consideration. So for mechanical advantage, we have losses in form of heat dissipation or losses in form of heat loss. Now, what happens is that due to the rotation of 2 or more parts, there is loss as a result of friction. Okay? So that is why the efficiency of a machine, the efficiency of an ideal machine may be 100%, but the efficiency of a working machine cannot be 100% efficient because there is work done against friction. Okay? All right. So let's see other forms of machines. Okay. Let's see the levers. The lever machine. Okay. Now, the lever machine is a rigid bar that pivots at a point. Okay. The lever has a rigid point. It's a rigid bar that is pivoted at a point. That means the pivoted means there is a presence of a support, which could be the what? The fulcrum, which is the fulcrum. Now we have various lever, first class, second class, and then third class. For first class, we can talk of maybe scissors, and the pliers. Here we can talk about the human arm. Then for the second class, majorly maybe the wheelbarrow. So for first class, we have scissors, pliers. Now for first class, that means the load is between the fulcrum. The load is between the fulcrum, which is the pivot, and the effort. That is for first class. Okay, a good example is your what? Is your scissors. Now what happened is that for the first class, okay, the fulcrum is between the load and the effort, something like this. Remember, it's an horizontal bar, it's a rigid bar. Bar means is horizontal, just like a beam. So we have a support, which is the pivot. This pivot is the fulcrum. So what we have the load. We have the load and the effort. So for first class, the pivot is between the load and the effort. So a very good example is your scissors. Let's have a sketch. Let's say we have scissors, for example. So here you apply force. Remember, force is same thing as effort. You apply force. So in between, there's this pivot. There's a pivot. Then here maybe your load. Here you have the load. Maybe this is a substance, an object you need to cut. Okay? So you have the load. So that means the pivot, which is the fulcrum is between the load and the effort. So in that case, this is a first class lever. First class lever. Therefore, second class lever, majorly you have the wheelbarrow. Okay. For the second class, you have the wheelbarrow. Let's have space. What happens is that the load now is between the fulcrum and the effort for second class lever. So we have our rigid bar. So our rigid bar. So let's assume you have let's assume we have a load. You have your load, and this is the fulcrum. And here you have the effort. So immediately you hold the handle of the wheelbarrow, you have the load in between the handle where you apply the force and the fulcrum. The fulcrum is where the wheel is, the tires. Okay? So second class, you talk about the wheelbarrow. Then for third class, the effort is between the load and the fulcrum. Okay? All right, so we also have, before we solve problems from the JAMB app, okay, examples under the third class, you talk about the baseball bat, the fishing rod, and so forth. So our major concern is that mechanical advantage, if it's greater than 1, if mechanical advantage is greater than 1, that means we are trying to reduce what? Effort. We are trying to reduce effort so as to what? Carry a very mighty load. So mechanical advantage is what? Load over effort. So if little effort is able to raise a very gigantic load, that means the mechanical advantage is greater than what? Is greater than 1. Then we also have a well in fetching water. Let's explain the wheel and axle in combination with the pulley. So let's assume you have this body. We have this body. So it's a bucket. So if this is bucket containing water, right? So this rope extends to this point. Okay? Then we have our wheel. Now at this point, we have, here we apply effort. That means you apply what? There's a force, apply force at this point. So what happens? You have the wheel. Immediately we apply a clockwise or anti-clockwise. Okay, let's say we have another rigid body. So entirely we have the well. Now, if you apply effort, there will be a rotation of the wheel. Now, if it's a clockwise, depending on the design, clockwise rotation may intentionally pull the bucket downward, while anti-clockwise is to move the bucket upward. Okay? So what happens is that we apply effort here, either a clockwise rotation or anti-clockwise rotation. By so doing, we have the wheel undergoing what? Rotation. Now, the numbers The numbers of, I don't want to use electrical terms because this is mechanical system. Now, you have what we call the pulley. This is likewise a pulley system. Pulley system in the sense that the mass of this water or the bucket is moving either upward or downward. That's the machine. Now, the rotation of the wheel reduce the effort. Reduce the what? The effort. There will be less effort needed for this bucket to move the water. Okay? So that is under the principle of the wheel and what? The wheel and the axle. Okay? Remember, load is also the resistance. Load is a what? It's a resistance. Okay, then we also have the screw jack. For the screw jack, what the screw jack does is that it converts rotational motion to a linear motion. Rotational motion to a what? To a linear motion. If I need to pull a car up, the screw jack, there's a rotation. The rotation of, while trying to wind the screw jack, what happens? There is a linear motion of the car. The car or the truck or whatever tries to pull up so that it will create an avenue where you can remove your flat tire. Okay, so the screw jack converts rotational motion to a linear motion. Because the screw jack mostly is for lifting off the load. Try to lift load. Okay, now what happens is that the bigger the wheel, the smaller the axle, then the greater the mechanical advantage. Because the mechanical advantage is also R over R. The big R is the radius of the wheel, while the small r is the radius of the shaft. Radius of the shaft. So when R is equals, if R is equals to R, that means the mechanical advantage becomes 1. So definitely in the machine design, the bigger the wheel, the smaller the axle. Okay? So that is why you have the wheel of the car is so large, while the shafts are so small, so that there will be easy rotation. There will be easy rotation. So if there's easy rotation, definitely there will be easy movement. Okay, let's see some problems. Some problems from our JAMB app. Okay, from the JAMB app, let's see some problem. Okay, we have a problem. Physics 2006. We have JAMB, Smacker. JAMB 2006. Question 15. It said, question, it said work done by load is always less than the work done by effort. All machine, that's point 1. Point 2, all machines are made up of levers, pulley, screw, and jar wheels. That is false, never. 3, a fishing rod is a machine. Yes, I made mention of the fishing rod, where the effort is between the load and the fulcrum. So that is third class lever. Now, effort is always greater than load. Which of the statements above about machines are true? So the correct answer is C, just 1 and 3. Work done by load is always less than the work done by the effort. It's less. Now, all machines are made up of levers, pulley, screw, jar wheels. No. We still have other forms of machines. Now, a fish rod is a machine which is third class. For third class, what happened? I told you earlier that the effort is between the load and the fulcrum. then effort is always larger than load. No, we have other cases where the load is larger than the effort. So which of the statements above about machines are true? So it's 1 and 3. 1 says work done by load is always less than the work done by effort, and 3, a fishing rod is a machine. So the answer is C, 1 and 3. 1 and 3. So let's see other questions. Okay, we have a question. This question is from 1992. We have a question from JAMB 1992, question 9. Question 9 says, a machine requires 1,000 joules. A machine requires 1,000 joules of work to raise a load of 500 Newton. Now, a machine requires 1,000 joules. That means that is work input. So it means the work input is 1,000 joule. Now, what you are imputing is always greater than your output, because the efficiency is work output over work input. Okay? The input is always greater than the what? The output. So work input is 1,000 joule. Now, he said a machine requires 1,000 joule of work to raise a load of 500 Newton. So we have resistance. Now, this is a mechanical resistance. Okay? Mechanical resistance, which is the load. Well, you might see other statements like resistance or mechanical load. Okay? Or I mean mechanical resistance, same thing as load, and that is 500 Newton. Now, it's needed to raise it through a vertical distance. So there is need for vertical distance. And the vertical distance is 1.5 meter. We have to calculate the efficiency. We know that efficiency is what? Work output over what? Over work input times 100 times 100% over what? Over 1. So in that case, we know that, so either you say work output, we can say useful. So efficiency can also be this symbol. This is symbol for efficiency. So efficiency. Now work output. For us to get work output, that means we know that work is force times distance. But this distance is a vertical distance. So we can use H. Because it's a vertical distance, we can use H. Now the work input, we already know, is 1,000. So efficiency is force 500 times 1.5 over what? Over 1,000. Now 500 times 1.5, that's approximately 750. Times 100% over 1. So we have this times 100% over 1. So 0 will cancel 0, 0 cancel 0, 0 cancel 0. So the efficiency is 75%. So it means the input, this means that 75% of the input energy is converted into useful work. 75% of the what? Of the input energy is converted into useful work. While the 75% has been lost. The remaining 75% has been what? Have been lost. So the correct answer there is B. Correct answer is option B. 75% of the input energy is being used for work, while 25% undergo loss. Loss in form of frictional losses, or either frictional losses or losses in form of heat. So that is JAMB 1992. Okay. All right. Let's see another question. Another question on the machine. Okay. We have this. We have another question. JAMB 2000 question 10. JAMB 2000 question 10. It said the velocity ratio of a machine is 5. We know velocity ratio. The velocity ratio is 5. It could be in the rotation. That 5 is gotten from the rotation of the pulley. Remember, the pulley is a machine, it's a simple machine used to lift load to a very high magnitude, to a very height, a large height. So we're told that the efficiency is 75%. Remember, these questions, they are coming from the JAMB, the O3 school app. So do well to install and activate for subsequent questions relating to machines. These are just, I'm just trying to show you that those questions, they are coming from the O3 school app. Now I say, what effort will be needed? Effort, we don't know the effort. Effort, we don't know. Then they say, what effort is needed to lift a load? So there's a resistance, which is the load. There's a resistance of 150 Newton. Okay? So that implies that efficiency, we know efficiency, this is a symbol of efficiency. So efficiency is also mechanical advantage, or let me just say mechanical advantage over velocity ratio times 100% over 1. We have various mathematical representation of mechanical advantage. So mechanical advantage, of efficiency. Efficiency is mechanical advantage over velocity ratio times 100% over 1. So if efficiency, what is mechanical advantage? It was not given, but we're made to understand that the velocity ratio is 5 times 100% over 1. Now the efficiency, that means the input energy that is converted into useful work is 75%. That means as a result of using that machine, what happens is that the 25% undergo what? Losses have been converted to heat. So we have 75% mechanical advantage over 5 times 100% over 1. Okay? So percent can cancel percent. We now have 75 equals to 100 MA. 100 MA over 5. So we can say 75 times 5 equals to 100 MA. Okay? Now, we know that 5 year is 1, 5 year is 20. Okay? So that implies that we're now left with 75 equals to what? 20 MA. So we have 20 what? 20 MA. So at the end, MA is 75 over 20. So MA is around, let's use our CAC. Using our CAC, that's about 3.7. So we have 75 divided by 20. Okay, it's about 3.75. So here, mechanical advantage is greater than 1. So whenever mechanical advantage is greater than 1, that means there is a reduction in effort in lifting a load. Okay? Because here mechanical advantage is greater than what? Is greater than 1. 3.75 is greater than 1. Now, the question did not say we should look for mechanical advantage. The question says, what effort will be needed to lift a load of 150 Newton with the machine. So this is what we'll do. This is what we'll do. There is a relationship between mechanical advantage. There's a relationship. We know that mechanical advantage is load over what? Over effort. Okay? So it's mechanical advantage is load over effort. Now we have load. So that means we have 3.75. The load resistance is 150. Here we can get the effort over 1. So effort becomes 150 over 3.75. So our effort becomes, we divide about 40 or so. So 150 divided by 3.75. It's about 40. Okay, about 40. So we have 40 Newton. 40 Newton. So the correct option there is B, 40 Newton. The option there is what? Is B. Let's move ahead. Okay. Now we have another question. 2004 question 11. 2004 question 11. Question 11. We have JAMB 2004 question 11. Now the question says that a machine whose efficiency is 60%. So efficiency is 60%. Has a velocity ratio of 5. Pulley rotation is 5. So velocity ratio. The velocity ratio is 5. Now, if a force of 500 Newton is applied, so there is an applied force. Applied force. Now, that applied force is in the form of what? Effort. And it's 500 Newton. 500 Newton. Now, it's applied to lift a load of P. What is the magnitude of P? So, load is P. Load magnitude is P. And this is unknown. So P is unknown. Now, we have applied force. We have velocity ratio. So that means that efficiency becomes what? Mechanical advantage over velocity ratio. Okay? Times 100% over 1. Now, efficiency is 60. Now, if efficiency, remember, the efficiency of, where you can get efficiency of 100% is an ideal machine. And practically, there's no ideal machine. For an ideal machine, the efficiency is 100%. But a working machine, like your fridge or AC, the efficiency can never be 100% because there's work done against friction. What happens is that there are moving parts of this machine that undergoes depreciation. So those moving parts undergo depreciation or wear and tear. So because of those wear and tear, the efficiency will reduce from 100%. So efficiency is 60%. That means the useful energy converted to work is 60%. While 40% undergo what? Losses. So efficiency, we have 60%. 60% equals to mechanical advantage. We don't know. So mechanical advantage over velocity ratio. If the velocity ratio is 5 times 100% over 1. Percent cancel percent. 0 cancel 0. So we are left with 6. 6 equals to mechanical advantage over 5 times, we still have 10 here, times 10. So 6 times 5, make it over 1. Make it over 1 mathematically. So we have 30 equals to 10 MA. So 30 equals to 10 MA. Okay, let me write this. MA. 0 cancel 0. So the mechanical advantage is 3. So now that the mechanical advantage is 3, that means there is an advantage because the mechanical advantage is load over effort. So we need a very small effort to raise a very large load. So what does that mean? The mechanical advantage is greater than 1. So there is reduction in effort, which is appreciated. So mechanical advantage is 3. We know that mechanical advantage is going to be load magnitude, mechanical advantage is load magnitude over applied force. And this applied force is our effort. We have effort of 500 watts Newton. So now we are asked to find the load. So here it becomes 3 P over what? 500. So definitely P, if we make it over 1, P becomes 3 times 0, you have 0, that's about 1, 0 Newton. So what do you observe? We observe that the load magnitude is greater than the applied force. So machines are designed in such a way whereby little effort can be able to raise a very gigantic load. So that doesn't mean that if mechanical advantage is less than 1, it's also appreciated. It's appreciated in the sense that there will be increase in speed. Maybe a machine that needs that whose speed move faster than its load, or whose speed, how do I put it? When the mechanical advantage is less than 1, it means that speed are being appreciated. That's what I mean. Okay, so here we have a load magnitude of 1,500 Newton being raised by effort of what? 500 Newton. So let's see the answer. Okay. The answer there is D. It's D. 1,500. So it's D. Let's see if we still have more question. Okay. We have a question from 2010. We have another question from 2010. Machine 2010. Now, we said that now from what we have solved, okay, we need a moving vehicle, for example, as a machine. We want increase in speed at some times so as to move faster. That's a machine. Rather than walking with our legs, rather than trekking, rather. Imagine bicycle and trekking, for example. There is a quite distinction. The bicycle moves faster than when a human trek. So machines are designed in such a way so as to make life comfortable, convenient for human beings. So machines are devices that makes work more easier and more convenient. All right. So now we have a question from JAMB 2010. 2010, question 10. It said, a machine of velocity ratio 6. So we have 2010, we have a velocity ratio. The velocity ratio is 6. Require an effort of 400 Newton. So effort applied. We have effort applied of 400 Newton. Okay? 400 Newton to raise a load. Of 800 Newton through 1 meter. So we have to find the efficiency. Find the what? Efficiency. So Now we know that efficiency, what is efficiency? Efficiency is mechanical advantage over velocity ratio times 100 what? Percent. Already we have the velocity ratio. Now what happened is that we need our mechanical what? Advantage. Now what is mechanical advantage? Mechanical advantage is load over effort. So since mechanical advantage is load over effort, load, what is our load? To raise the load through 1 meter. So load is 800. Effort applied is 400. That is 2. So it means that mechanical advantage is equals to 2. We need an effort of 400 to raise the load of 800 Newton. There is mechanical advantage because there is a reduction in the effort that is being applied. So now that mechanical advantage is 2, we need the efficiency. What is the efficiency of that machine? What is the efficacy of that machine? How efficient is that machine? So efficiency, we have efficiency, MA over velocity ratio times 100% over 1. We know that mechanical advantage is 2. So that means efficiency is 2 over what? Over 6. Because the velocity ratio is 6. So 2 over 6 times 100% over 1. So 2 here 1, 2 here 3. So we have 100 over 3%. That's about 33.33%. Okay? So the correct answer there is C. 33.33%. Okay. Then we have another question. We have another question from JAMB 2005, question 9. Question 9 says, in an ideal wheel, once you see ideal wheel, it means there are no losses in such kind of machines. Okay, it's not a practical machine, it's just an ideal wheel. In an ideal wheel, an ASU system, R stands for radius of the wheel, and small r there is the radius of the ASU. We have wheel and ASU, they go together. What is the mechanical advantage? Okay, the mechanical advantage is R over R. We said it before. Now, if R is equals to R, what happens? It means the mechanical advantage, okay? It means mechanical advantage, R over R, let's say is 1. That means 1 over 1. Mechanical advantage is 1. Now, if mechanical advantage is 1, that means there's no losses. There's no what? There's no losses. There's no losses. It's an idea, it's not a practical what? Machine. Okay? For practical machine, it means there is no gain. Mechanical advantage is no gain. So it means that the efficiency is just 100%. It's 100%. So mechanical advantage here is what? Is 1. So it's R over the radius of the wheel over radius of the ASU. Okay? All right, we have another questions. So the correct answer here is R over, check your option there, R. So that's B. Now, another question again is JAMB 2019, question 13. It says calculate the velocity ratio of a screw jack of a pitch 0.2 centimeter if the length of the bar is 23 centimeter. Okay, velocity ratio, we know velocity ratio is 2 pi L over P. I wrote it at the beginning of the session of the class. So velocity ratio is 2 pi times the length there is 23 centimeter. That's the length. Then the pitch is distance between the thread. So that's about 0.2. So VA, we have 2 pi. If we check, okay, let's use our calc. So we have 2 times 23, that's 46. 46. So 46 pi over 0.2. So VA, okay, yes. So divide by 0.2. We have 230. So 230 pi. So this is the velocity ratio. So the correct answer there is A. Correct answer there is A. Okay, let's also check our WAEC app if we can see some other questions. We have WAEC. We also have question from WAEC. From WAEC, we have WAEC 2005 question 6. Objective. Is that which of the following simple machine is a second class? I'll be saying it at the beginning of the class. Is that which of the following simple machine is a second class? What happened to second class? You have something like this, like this, like this, like this. So we have the fulcrum. Let's say we have here to be the fulcrum. Then you have the load. You have the effort. So this is second class. So the answer there is wheelbarrow. Is wheelbarrow. So you have your load here. There's a resistance here. Resistance. Why are we saying resistance? Why are we saying resistance? For example, if you have much load on that wheelbarrow and you try to push the wheelbarrow, because of much load in that wheelbarrow, to be so difficult for you to move. So it's resisting your movement. That's why we refer the load to be what? To the resistance. So this is load, which is resistance. Now we have the fulcrum. The fulcrum is where you have the tire, the wheel. Then the effort, here you have the handle. Handle, let's say here is where the tire is, and the wheel and so forth. Okay, the tire causes the rotation. But what happens is that the handle is where you have the applied force. The applied what? The applied force. So we have several options there. Scroll bar, claw hammer, seesaw. So the correct answer is a wheelbarrow. A wheelbarrow, the load is in between the pivot, which is the fulcrum, and the force. The force is the effort. So that is WAEC 2005, question 6. Okay. Now we have this one, they are basic. WAEC 2023, part 2, question 9A. It said define each of the following terms used in simple machine. Pivot is often referred to as fulcrum. They say we should define pivot. Fulcrum is the same thing as what? Pivot. Create a support. So pivot often refers to as fulcrum is the point or axis around which a simple machine, such as a seesaw, can rotate. And this is a pivot. Now I can have a load here. Then it's going, this bar, this horizontal bar, a rigid bar, will be going, if I apply a mass here, apply another mass here, let's say here is 20 kg, and here is 40 kg, here is 2 centimeters, here is 4 centimeters. So what happens is that this is the pivot. At this pivot is where the rotation takes place, either going clockwise or anti-clockwise. Either going clockwise or anti. Now another one said 2023. So we have another question. 2023. Part 2, question 9. Part 2, question 9. A. It says define each of the following use in machine with efficiency. We know that efficiency is how effectively a machine can carry out its tasks comfortably or what? Effectively. What is the efficacy? What is the efficiency of that machine? How is it able to perform that work? So we know that it's useful work done, okay? Efficiency, useful work output over what? Useful work input, okay? Times 100% over 1, times 100% over 1. Now, another question there says, draw a diagram of a pulley. I think this one is 1997. 1997, question 1B. It said, draw a diagram of pulley 5 system, of velocity ratio. So we have pulley system whose velocity ratio is equals to 5. So let's see. Say we have a rigid body. Okay, let me stop here. Borderline. 1, that's the first one. 2, 3, 4, 5. Okay. So here is where you apply the effort. Just like the wheel and the axle we drew for the wear the other time. If the number of rotation becomes 5, 1, 2, 3, 4, 5. So that becomes the velocity ratio. Because at that point, the velocity ratio becomes what? Effort over what? Overload. Effort overload. Okay. If they ask you to sketch for 3 systems, you stop at 3. 1, 2, 3. Okay. All right. Remember, this video is brought to you by O3 School, and our major target is to make 300 plus for all our students all over the federation to have 300 plus in their JAMB. All other subjects, they are quite available. Your biology, your government, we have them in the app installed for you. Do where to install and also what? Activate. For subsequent videos and questions, it's quite available on the app. Today, we are just made to know a little surface about machine, how machine works. Okay, a kind of recap though. Now, machine they are just tools that enable work to be done effectively, and with the major terms used in machine, mechanical advantage and the velocity ratio. Now, we say if the mechanical advantage is equals to 1, is an ideal machine. So that means there is no mechanical, there's no gain. There's no gain. The machine is just ideal. But when the mechanical advantage of the machine is now greater than 1 as a result of useful work, that means a little effort is needed, is available to raise the very gigantic load. And we saw that in the various questions that we have solved. Okay? One of the examples is that for the screw jack, the screw jack is a machine that is needed to lift a car up so as to remove your flat tires. What happens is that the little effort from the screw jack is able to lift a very gigantic load, which is the car or the truck, or rather. So those were the, we also said that the velocity ratio can be obtained from a pulley system. So here we have a rotation of maybe from a rope, rather. So we have 1, 2, 3, 4, 5. So the number of rotation tells us the velocity ratio. Thank you. Please do well to activate the app. See you other time.